Good afternoon everyone. I am Chanda Devnath, one of the PMRF fellows. So I am pursuing my PhD from IISER Berhampur, basically in organic synthesis and catalysis. So here I am TA of this course, Mechanisms in Organic Chemistry, instructed by Professor Nandita Madhavan. So this is our live introduction week class week 6. So if you guys want to know about the other classes, you can go and check my videos which have been uploaded in my YouTube channel, and I hope NPTEL has provided the link also. From there you can go and check so that you can get an idea and can solve more questions from this topic. So let's start. So here I will give a recap of the previous class where I have discussed Hammett equation and other plots of that. Then we discussed about deviation from LFER theory and also solvent effect on reaction kinetics. Then we started our topic kinetic isotope effect and discussed about primary kinetic isotope effect. So then based on the Hammett equation we are solving some problem like how, depending just getting the rho value, how can we determine mechanism of a reaction. Rho value can determine by just determining the rate constant of a reaction, rate of the reaction, and putting it on the Hammett equation by log k by k0 equal to rho sigma. From there you can get the value of rho from the slope of the graph, and from the value of rho you can determine the mechanism. So here one question I gave to try by yourself. So let's solve that one first, then we will commence today's class. So here one reaction is given and the rho value is also given. It is minus negative rho value. In the last class I have told several times that whenever there is a negative rho value, that means our involved intermediate is positively charged, because the Hammett equation is based on the deprotonation of carboxylic acid, where we are getting the intermediate is a negatively charged, and based on the stability of the intermediate we are getting the rho value, and in that case rho value was positive. I hope you guys can memorize, or if not you can go and check. So now whenever the rho value is negative, that means reverse case is happening, because whenever rho value is positive means a negatively charged intermediate is forming. Now here the rho value is negative, that means our intermediate formed is a positive. So how can this possible? So our intermediate is positive, and by addition of electron donating group the reaction rate increases as it is high negative value. High negative value means as like that, in high positive value means when we are adding electron withdrawing group, that intermediate gets stability. Similarly, whenever in case of negatively charged, our intermediate is positively charged, and if it is high negative charge, that means by adding electron donating group our intermediate gets some stability. That's why the rate enhances. So whenever there is a negatively charged rho value, it means by electron donating group rate increases. Okay, and by electron withdrawing group rate cases. Okay. So based on that, if you can determine the mechanism, a positively charged intermediate will form. So just first we will remove the leaving group. So primarily carbocation, and if we add electron withdrawing group, what will happen? That will donate electron to this position and it will get some stability. After that, this ethanol here, sorry, then we will get our desired product. Okay, let's go to our next question. So it is based on primary kinetic isotope effect. So what we have done in case of primary kinetic isotope effect, whenever there is a proton or CH bond gets broken at the rate determining step, that case if we substitute the CH bond with a CD bond, that is a deuterated bond, there is a change in rate while changing the proton with a deuterium. As CD bond is stronger than CH bond, therefore while having CD bond the reaction rate decreases, because to break a CD bond we need more amount of energy and time. That's why whenever the substrate having a CH bond react faster than that of a CD bond. So that's why in case of primary kinetic isotope effect, KH rate of hydrogenated compound is greater than the deuterated compound. So if anyone wants to show, so here they haven't mentioned it is a primary kinetic isotope effect, but they have mentioned that it is a non-zero kinetic isotope effect. That means it will have a primary kinetic isotope effect. So to have a kinetic isotope effect, the proton should be broken at the rate determining state. So here, if you can see, this is what kind of mechanism. This reaction will go through this is a known reaction, as there is a double bond is forming, so this reaction will go through a elimination type of reaction. Now there are three types of elimination. One is E1, E2 and E1CB. So there is three type of elimination: E1, E2 and E1CB. So whenever there is a E2 elimination or E1 elimination, what happens? No kinetic isotope effect. Why? Because in case of E1, first the leaving group leaves from the system. After that, the CH bond gets broken, which is not the rate determining step. In this case, the first step is the rate determining step. That's why in case of E1, no kinetic isotope effect is observed. Now if we go to the E2, in this case this is a concerted reaction or a single step reaction. That's why the CH bond and the leaving group elimination happens in a single step, and that is our rate determining step. That's why here we can see kinetic isotope effect. The last one is E1CB. In this case, what happens? First, the hydrogen gets removed. Hydrogen gets removed. After that, the leaving group gets removed. In this case, the second step is the rate determining step. In this case, the second step is our rate determining step. So that's why it will also not show any kinetic isotope effect. Okay. So therefore, let's see which of in all the cases double bond has formed. So that means in all the cases eliminations have been take place. So if we go through the mechanism, then you can understand where kinetic isotope effect will be observed and where not. So what will happen? It will get H plus from the acid and get removed from the system. First, it will get H plus and get removed from the system. Due to that, it leads to a formation of carbocation. After that, there is a proton adjacent that will come here and we will get our desired product. Now in this case, as we have known from the E1 equation, this one is our RDS or rate determining step. So in this case, no CH bond has been broken. That's why it will not show any kinetic isotope effect. In this case, what is there? There is a CH. This is A2 type of elimination. So this will come here and it will be removed from the system. So this is this form. So it is the only step and this is our rate determining step. So this will show kinetic isotope effect. Next, this one. In this case, as the leaving group is a bad leaving group, so we know what is A1CB whenever there is a bad leaving group. It will not get removed easily and no H plus is given like this one. Only basic condition is there. So there is a proton which is highly acidic. Acidic. So this OH minus, take this proton and generate a carbon ion. Then this carbon ion comes here and OH gets removed. from our desired product. In this case, our second step is the rate determining step, where no CH bond has been broken, so it will not show any kinetic isotope effect. So which will be our answer? Answer 2, only B. So this question came in December 19. So now you can understand, as you have learned what is kinetic isotope effect. So if any question come from kinetic isotope effect, you can easily attend those. So there are some other types of kinetic isotope effect beyond primary kinetic isotope effect. That is secondary kinetic isotope effect and kinetic solvent isotope effect. So let's go to the secondary kinetic isotope effect. So what is secondary kinetic isotope effect? A secondary kinetic isotope effect is observed when no bond is isotopically labeled atom in the reactant is broken or formed. What does it mean? Suppose a reaction where carbocation gets generated, but to compensate that one, when any CH bond is broken, that is not getting broken at the rate determining step. In that case, the presence of the CH bond or the CD bond will affect the reaction, but not as much high as primary kinetic isotope effect. So in that case, it is called as a secondary kinetic isotope effect. So where it is observed when there is a reaction where the CH or CD bond is not getting broken at the rate determining step, that is called secondary kinetic. That will show secondary kinetic isotope effect. When it is observed when there is an isotopic substitution at alpha or beta position of the reacting center, then it may show kinetic isotope effect. The steric effect on bending vibration as CH bond is longer than. Why this is observed? Because if you see that the bond length of CH is greater than that of the CD bond. Because of this greater bond length, whenever there is an adjacent reacting center, it creates a steric effect less than that of the CD bond. So that's how it affects the reaction rate of the reaction. So now there are two types of secondary kinetic isotope effect. One is normal secondary kinetic isotope effect and another is inverse kinetic isotope effect. So how secondary kinetic isotope effect is observed? If you see sp3ch bond, if it can move, as bonds have some energy in it, so whenever there is a bond or molecule at room temperature, it continuously move or vibrate. So if we see the vibration mode of this CH bond, in plane vibration it can vibrate like this way and this way, and out of plane it can vibrate just out of this plane, like suppose the CH is coming out of the computer screen or your mobile screen, the CH is coming out of the mobile screen and again going back to the mobile screen. Okay, that is out of plane bending. So how it, if you want to show, if we show it like a bold arrow, suppose this is coming out of your mobile screen, the CH is coming out of your computer screen and again going back to the computer screen, that is out of plane bend. Now how CH sp2 bond can rotate, bend? In case of in plane bend, it can bend like this way, and if in case of out of plane bend, it can bend similarly, is coming out of the plane and going back to the plane. So this is very less in case of sp2ch. In case of sp2ch, this type of out of plane bending is quite less, because sp2 bond can't go, it can rotate like this way, but the out of plane bending is quite not feasible. So this is probability of this out of plane bend is quite less. Because of that, the compound gets some stability. Because of that, the compound gets some stability. So whenever a reacting center, if sp3 center goes to the sp2, so what happens whenever there is a so now if instead of CH there is a CD bond, what will happen? This type of bending, during this type of bending there is a steric hindrance between the other bonds. But in case of CD bond, due to shorter length of the bond, the bending will be less. Due to shorter length of the CD bond, the bond bending will be less. So therefore, the bending will be therefore whenever a reaction, therefore its energy will be less. Therefore the energy will be less. But in case of sp2, similarly as CD, so the bending in case of CD, the bending will be less. So whenever any reaction goes from a sp3, but now in comparison with sp3 and sp2, which has less bending? The sp2 has less bending. Because in case of sp2 there is no out of plane bending. In case of sp2 there is no such out of plane bending. So in case of sp2 there is a less energy. So whenever there is a sp3 compound, the energy will be always higher than that of the sp2, because the bending mode is greater, the bonds are highly excited, can highly bend. But in case of sp2, the bending mode, the out of plane bending modes are not there, so the bending will be less, so the energy will be less. Now in comparison with CH and CD, we know as CD bond is smaller, so there is also a strain in bending. That's why CD bond will bend less than CH, so that will also have a less energy. If we see the graph, you can see the CD has less energy rather than CH. The CD has less energy than that of CH. Now suppose the reaction takes place where the sp3 goes to a sp2 sorption state. Here the sp3, here the carbon is sp3 hybridized, goes to a sp2 hybridization state. What happened in this case? In this case, the energy will decrease as from sp3 to sp2 there is a reduce in bending mode, so energy will decrease. Now, as in case of CD, due to shorter bond length, the energy will decrease greater than that of CH, while therefore you can see while going now in case of if sp3 is going, as CH bond is getting involved, so CH bond will react faster, so the rate of the reaction will be greater here. So that's why if it goes here, you can see the energy difference between for CH is less than that of the CD, because the CH bond get reduced, because of the loss of bending. That's why it will show a normal kinetic isotope effect. As KH is greater than KD. Now suppose a reaction where sp2 hybridized carbon is going to a sp3 hybridized carbon. A sp2 hybridized carbon is transforming to a sp3 hybridized carbon. So what will happen in the reverse case, as in sp3 the energy of the CH get enhanced because of the incorporation of the out of plane bending mode. Due to that one, the CH energy will increase in greater extent than that of the CD. The CH energy will get greater extent than that of the CD. Therefore, the energy gap between CH get enhanced than that of the CD, which leads to the rate of the reaction get reduced in case of CH. So CH reacts slower than that of the CD. In that case, we will show a reverse kind of reaction where the so it will be less than 1 because it will be negative, as KH is greater than KD. So it will show an inverse kinetic isotope effect. So KH, whenever this is normal kinetic isotope effect, means KH will react faster, that is KH greater than KD. And whenever there is an inverse kinetic isotope effect, that means the KH is less than KD. If we see this example, what is happening? Just think, then I will just give 1 minute. What they have given? They have given the KH by KD value of both of the product, and they asked why this type of case is happening. So just try, I will solve. So what is happening in this case? So what is happening in this case? You can see the first case, substitution is taking place. The first case substitution is taking place and second step elimination is taking place. So how is this possible? We place support. If there is a CH, if it comes here, gets removed, what we will get? We will get the eliminated product. Now another probability is the substitution, where this chloride gets removed and you will get the carbocation. And after that methanol will attack again and form our and forms our substituted product. Okay, understood? Forms our substituted product. Now, what is the K? This K is by Kd value determines. So, in this case, you can see there is a Kh by Kd value less than 1. So, when we will get a Kh by Kd value less than 1? When there is a secondary kinetic isotope effect. And whenever there is a 1 greater than 1, that means there is a primary kinetic isotope effect. So, in this case, substitution reaction, this means that our hydrogen bond is not getting broken at the determining step. Whereas in this case, our CH is get broken at the kinetic isotope at the determining step. So from that it can determine. So you can, if you see the mechanism here, this one is the rate determining step. So thus very easily you can determine that our CH bond is getting involved at the rate determining step. That's why it will show a high kinetic isotope effect. But in this case, we know that SN1 reaction, the first step is the rate determining step, and in this step the CH bond breaking is not taking place. It's just removal of the leaving group. Whereas the carbocation stability depends on this CH bond. The carbocation stability depends on this CH bond. So due to higher length of the CH bond, this can help to stabilize the carbocation in a greater extent. Therefore, it somehow enhances the rate of the reaction where KH therefore KH is greater than KD little bit because to stabilize the carbocation to stabilize the carbocation. Okay, understood? So whenever the CH bond is getting broken at the rate determining step, it will be a primary kinetic isotope effect. If it is not, but it helps to stabilize the reaction or stabilize the intermediate, it can affect the rate of the reaction somewhat. That's why it will show a secondary kinetic isotope effect, which is a positive value but not greater than 1. And whenever there is a negative value, it means inverse kinetic isotope effect. Okay. So here you have to explain. Here 3 reactions are given and their kinetic isotope value. So you have to explain why they are showing this type of kinetic isotope value. From the value you can see all are primary kinetic isotope effect, as all are greater than 1. So all are primary kinetic isotope effect. So how can you explain? Just try the first one. Try the first one. I will answer. Try the first one. I just give 5 seconds. So what will happen? You can see there is a formation of radical. There is a formation of radical. This Br radical will abstract this proton and generate this benzylic radical. So this is just proton abstraction. Therefore, this happening. This is a rate determining step as the proton abstraction is taking place. So it will show a primary kinetic isotope. This is a single step process. So therefore, it will show a primary kinetic isotope effect. Now, what will happen in this case? This CH will go here. So this CH is directly involved at the reaction. So therefore, if we replace the CH with the CD, there will be a reduction in the rate of the reaction. Therefore, it will also show a primary kinetic isotope effect. And there is the last one which we have solved previously also. It comes here, kind of E2 elimination. Therefore, it will show a primary kinetic isotope effect. Okay. Now, this is a similar type of reaction. So, deuterium kinetic isotope effect for a reaction was found 4. So, it is greater than 1. So, that means primary kinetic isotope effect. Based on this information, mechanism of the reaction is which one? E1, E2, E1Cv or free radical. As you have known, I have discussed just some slide before that if it is E1, there will be no kinetic isotope effect. If it is E1Cv, there will be no kinetic isotope effect, and there is no such of chances of free radical formation. There is no such case can possible here. So the only option is available, that is E2. And how this is taking place? This will come here and this will be removed from the system. Okay, so what will be our correct answer? Correct answer will be E2. This question came in CSIR NET December 2013. So now whatever question comes from the kinetic isotope effect, I think it will be easier for you to attempt. So there is another question. This is from Clayden. So what they have asked, the hydrolysis of oxygen in 0.1 molar sulfuric acid has Kh by Kd value 0.7, that is less than 1. That means secondary kinetic isotope effect. And the entropy of activation is minus 76. Suggest the mechanism. So for based on these values, you have to suggest mechanism of the reaction. Just try. what will happen? The hydrolysis of this, so here it will show a secondary kinetic isotope effect. So there will no CH bond will involve from the H2O at the determining step. So what will happen? First, there is be, as it is shows a primary kinetic isotope effect, a secondary kinetic isotope effect, that means, and the entropy is negative, so that means there is no involvement of CH at the determining step. So there is a possibly a reaction is going through a stepwise process. It's not a single step process. It's not a single step process. So what will happen? This oxygen ring will open. Now what will happen? Now this is our determining step. Now next step is H2 addition. So this will be our, when the nucleophile attacks to this carbocation, we will get this one. Rest will be same. So this can take up this proton. Next, so it comes here. I get our desired product. We get our desired product. Okay, I hope it's clear. Now, how we can explain the secondary kinetic isotope effect in this case? You can see this is our rate determining step. Now, if we substitute this H with the D2O, if we substitute the H with the D2O, now the CH bond is getting broken at this step. The CH, here there is a breaking of CD bond, then it will affect the rate of the reaction somewhat, because if it is CH bond, that will be broken by this N lone pair in a greater extent or faster than that of CD bond. So therefore it affects the rate of the reaction little bit, whereas CH will break easily and will get our desired product. You understood the mechanism, right? Okay. This is simple. So from the Kh by Kd value, now we can determine the mechanism of the reaction. Whenever you can see a secondary that is less than 1 value, you will go for a stepwise process or a process where the CH bond is not involving in the determining step. This is another question I will give. This is also from Clayton. You can try and get a idea. I will solve this one in the next class. What they have asked, these two reaction, you can take a screenshot or save this, so that take a picture of that one, so that you can solve it and try to solve this question. I will get back to this one in the next class. Okay, let's go to the next slide. So what they ask, the reaction that show a primary kinetic isotope effect for isotopic substitution of the marked hydrogen with deuterium. So among this reaction, if the marked hydrogen has been substituted with deuterium, which one will show, or which of these will show a primary kinetic isotope effect? That means Kh by Kd value will be greater than 1. Primary kinetic isotope effect means Kh by Kd will be greater than 1. Okay. So let's think. This is a simple Diels-Alder type of reaction. If it comes here, will form this type of cyclohexane ring. Now see, in this case what is happening? There is no loss of CH bond. There is no loss of CH bond. What is just happening? This carbon hybridization, this carbon is sp2 hybridized, whereas in this case this carbon is sp3 hybridized. This is the only difference. So when you know there is a change in hybridization, that will show secondary kinetic isotope effect. So that will only show a secondary kinetic isotope effect. Let's go to the next one. In this case, how this is a one kind of electrophilic substitution reaction. So what is happening? This type of, this one we have solved earlier also when we were discussing about electrophilic substitution. In case of bromination reaction, what happens? This is double bond will attack here, and this will break and goes. So you get this type of intermediate. This CH will come here, and through aromatization we'll get our desired product. Now in this case, the first step is the predetermining step. The first step is the determining step. So here you can see there is no CH bond breaking. CH bond is getting broken in the next step or second step. So it will not show any primary kinetic isotope effect. In this case, this one we have done earlier also. This is a similar simple alpha bromination. It will go here. Again it comes here back, and that will trap 1 Br plus. So it is a, in this case, we draw the reaction. draw the reaction. This type of enol will form, this type of enol will form, and this is not this type of enol will form. After that, what will happen? After that, what will happen? As there is a Br2, this comes here, and this takes one bromine, and from that one we get our desired brominated product. Brominated product. So in this case, this step is the rate determining step. So from this one you can see each bond is getting proved at this step, so that's why it will show a primary kinetic acid of Fe. Now next one is the allylic bromination. Whenever NBS is given, what will form? That will form a radical this will give a radical this gives us Br dot. So this Br dot will take up one generate CH2 dot and that will take another Br dot and will form our desired product. In this case, this step is the RTS. So that will show a kinetic acid of Fe. So in this reaction, the last two will show kinetic acid of Fe. The next topic we will discuss here, that is heavy atom acid of Fe. So whenever we are just till now we have just discussed about kinetic acid of effect regarding KH and KD, where the hydrogen atom is getting replaced by a deuterium. Now suppose any other atom get replaced, like carbon or any heteroatom, chlorine, bromine, that get replaced by its isotope. What will happen in that case? In that case, whenever there is a heavy atom get replaced, then due to high mass value, there is a very change in potential energy or vibrational energy. There will be very less change in potential or vibrational energy. Therefore, in that case, the kinetic acid of effect will be very small. The kinetic acid of effect will be very small. So to determine that one equation was given, this one, where this R equals to the percentage R equals to the percentage of heavier isotope equal to at t time t, where this is heavier isotope at t equal to at t equal to 0. So in this case, by this equation, we can get the kinetic isotope effect for this heavier atom. Now let's go. If we see the scenario, suppose a case where in equilibrium there is a substrate, there is a mixture of substrate with a heavier atom and a mixture of substrate with a deuterated bond and a hydrogenated bond. Now they are in equilibrium. Now a reaction is taking place. Suppose a reaction where the CH bond energy both of the bond energy get reduced. But in this case, if the CH bond gets reduced in greater extent, suppose a reaction where the CH bond gets reduced in greater extent than that of the CD. So the energy difference between CH and CD get reduced. In that case, the hydrogenated substrate will react at a faster rate than that of the CD. The hydrogenated substrate will react at a faster rate than CD. And suppose if after a reaction in product, the CH bond energy get enhanced. Suppose after a reaction when the CH bond energy get enhanced than that of the CD. In that case, the deuterated product react faster than that of the CH. So this is the equilibrium isotope effect. So based on that, if we solve this question, so this type of cyclohexane are in equilibrium. Now, when two axial bonds are there, is a huge 1,3 diaxial interaction. So there is a CH interaction and interaction with one CH bond. So this prefers to rotate and stay in a di-equatorial form where there is a no interaction. Now suppose one product which is 2 CH3 in axial, 2 CH3 in equatorial. Now if we flip it, we get structure while again 2 CH3 in equatorial and 2 CH3 in axial. So here it will stay as a 50-50 because both are equally stable. Both of the substrate are equal in energy, so they will be in 50-50. And whenever if you take at NMR at room temperature, then what will happen? Due to flipping of this fast flipping of this ring, this CH3 in this structure, this CH3 is axial, whereas in this CH3, in this structure, then this CH3 is equatorial. Therefore, there will be both the CH3 in axial and equatorial. Both the CH3 in axial and we will get one distinct peak. We will get one distinct peak for both the CH3 in axial equatorial. But if we take a room NMR at very low temperature, what will we get? Both the CH3 at a different delta value. Now suppose if we substitute one CH3 with a deuterium, with deuterated compound, what will happen? After flipping, this CD3 will go downwards. Now due to less bond length of the CD, it will be less expanded in the space, therefore it will suffer less interaction with this CH3 bond, which makes this structure more stable, than that of the B in case of CD3. in case of CD3. Therefore, it prefers to stay in this form. There, in that case, this axial CH3 and this equatorial CH3 will give two different peaks because they are less abundant, they are less flexible to go for ring free peak, and this CH3 is less flexible to go in the equatorial form. Therefore, it will distinctly give a peak for its axial form, and another CH3 will give a distinct peak for its equatorial position. Okay, I hope it's clear. So whenever there is a sigma plane, or symmetry in the compound, then two peaks will give same NMR in same position in the NMR spectra. But if there is no such symmetry in the compound, then the two hydrogen will give a different peak in the. So from this one we can explain the equilibrium isotope effect. Because of this isotope effect, the equilibrium shifts towards the left hand side. Because of this CD3 isotope effect, the equilibrium of the cyclohexane shifts towards the left hand side. Whereas in case of CH3 it was in 50-50. So this is called equilibrium isotope effect. Next topic which we will discuss, that is isotope labeling. So suppose we have labeled we have taken a substrate and we have labeled one of the atom with its isotope. It's not labeling, we have substituted one of the atom with its isotope. From that one we have labeling that one. Suppose in this case we are taking normally carbons are carbon 12. Now we are taking this substrate where this carbon is no more a carbon 12, where it is carbon 13. That is, we have substituted this carbon with this isotope. So from the product we can determine the mechanism of the reaction. So if you try to determine the if you want to get this product, what will happen first? So this OH will attack at this position and NH2 will remove and will form this type of phthalic anhydride kind of compound. After that, this OH2 will attack this opens up and form our desired product. Now from you can see another possibility is attack to this bond. In that case also we will get this product. In that case also we will get this product. In both of them this carbon atom is marked. In both of them this carbon atom is marked. So from this one, by just seeing the product of the compound or the labeling one isotope from substrate to product, we can get an idea of the mechanism of the product. We can get an idea about the mechanism of the product. Now based on that, let's try to solve this one. So they have asked to draw a mechanism to account for the following reaction that scrambles with the isotope labeling. So they have taken two substrates. It's a simple disorder reaction for diene and dienophile, and they have labeled the two carbon of the dienophile and when they got the product, they again got a dienophile and diene, but in this case the diene got labeled by this isotope carbon. So how this is possible? We have to determine the mechanism. How this reaction, this labeling of this isotope from substrate to product is possible. I just give 10 seconds try, then I will solve it for you. So what will happen? Simple, first Diels-Alder reaction. This one comes here. So what will come? This is the dienophile part. And this is our diene part. This is our diene part. And this is our dienophile part. Now what will happen? The next step, what will happen? So to get this cyclohexane, there should be a removal. So how is this possible? So suppose this ring breaks not from this position but from this position. Then it is possible that whatever dienophile is gets removed, there will be a reverse Diels-Alder reaction. Reverse there will be reverse Diels-Alder. So what will we get? So this bonds comes here. So what is we are getting? Here we are getting a triple bond. And again we draw how it looks like. We are getting a double bond at this position and this is, so we are getting these two carbons are labeled. So here from the just product we can get an idea that first a Diels-Walder reaction is taking place, after that a reverse Diels-Walder reaction will take place. Okay, let's go to the next question. So they asked to explain why not this one. Why? So they have marked this oxygen. So they have marked this is just normal ethanol. So it's normal ethanol type of reaction where this oxygen is marked. So they have asked why we are not getting this one but this one. So from this one you can see there is an incorporation of marked or isotope, oxygen isotope in the system, and removal of, from the product you can see there is a incorporation of marked oxygen, whereas this oxygen gets removed from the system. But in this case this oxygen is already in the system, whereas the marked oxygen is outside. So you have to imagine or you have to predict the mechanism where this oxygen can be incorporated. So there are two types of mechanism is possible. We go to the first mechanism where we are trying to draw both of them equally so that with a different color, so that you can, it will be easier for you to determine how these reactions are happening. So just by labeling the isotope we can get an idea about the reaction mechanism. I am not drawing the 18 because it's already red color, so from that you can get an idea. The yellow colored oxygen means the normal oxygen, and red colored here means the isotopic oxygen. Now one probability is this. And another probability is so what will happen? This is step 1. This is some one probability, this is another. So if we try to draw the mechanism or the product, so in which mechanism we can see red oxygen in the substrate in the product? In the which mechanism we can see the red oxygen in the product? Mechanism 2. So what will be the mechanism of this esterification reaction? Mechanism 2, where the ester is acting as a nucleophile. where the ester is acting as a nucleophile. In this case, the acid was acting as a nucleophile. So which one is preferred here? This one. So our preferable mechanism will be mechanism 2. Okay. So for the first time, if you are having any doubt, try to draw all the probable mechanism. Then from that one, just try to find which one is supporting your outcomes. So the last topic which we will discuss, and this one we will continue in the next class also, that is intermediate trapping. So to know the mechanism of a reaction, we can trap the formed intermediate in a system. In a reaction, if we can trap the intermediate, we can get an idea how the reactions is taking place. So suppose in this reaction, there are two types of base is given. One is LDA, another is ET3N. Now there is two possible CH bond is there. One is this one, another is this one. So this CH can goes here and this open, and this O minus will take TMS from this position. Okay. So now what type, in which case which TMS will take up? You can see whenever there is a ET3N, this CH goes here, this goes here, forming the intermediate O minus. So here as a trapping reagent we are using TMSCl. As a trapping reagent we are using TMSCl, and by just trapping this intermediate, when we get the product, we get this one as a measure. From that one we can get the idea that whenever ET3N is given, more substituted CH bond will get involved and give us this type of more substituted enolic intermediate. Whereas in case of LDA, this less substituted CH bond get involved and give us this less substituted enolic intermediate. And as a trapping reagent we are using TMSCl, which trap and give us this product, and by watching the product, by observing the product, we can determine that in case of LDA this type of intermediate is formed. So by just intermediate trapping, by using any reagent, we can trap the intermediate so that we can get an idea which type of intermediate is taking place. Then from the intermediate we can get an idea which part of the reaction or which part of the substrate is getting involved in the reaction. Okay. So in case of ET3N, which hydrogen will take place? Whenever your ET3N is given, you have to substitute the internal CH, and whenever LDA will be used as a base, you will substitute the external or less substituted CH bond. So now suggest the mechanism of this reaction. This thing, this normal aldol deprotection reaction, because this is acetal. Or ketal. This is ketal. So just by deprotecting we can get this ketone. So how is this possible? One probability is this one. First, this will take up H plus, then O minus can remove one of the OR from the system, and again another H2O will attack and remove one OR from the system. Another mechanism is this one, that first H plus will take up by the OR, then then water will attack directly to remove one OR from the system, and again just by assistance of this OH one word will get removed from the system. So among this one, which mechanism is possible? So in one case, the carboxylium, a oxocarbonium intermediate is formed due to, as in this case, the nucleophile is not directly removing the OR. Nucleophile is first attacking, then first this OH will get protonated and get removed from the system by the internal nucleophile. Whereas the OR is getting removed by the external nucleophile in the first step. So which will be possible? So if we see, try to trap the intermediate of the oxonium intermediate by a oxocarbonium intermediate by a sulfide dianion, we can see the formation of this type of product taking place, which supports that there is a formation of carbonium intermediate which is getting attacked by the sulfide anion and form this type of product. So this achieved in 97% trapping, and rate constant for the acid catalyzed cleavage of the ketones are independent of SO3 2-. So conclusion, SO3 2- is not present in the transition state of the rate determining step. So the reaction proceeds to a oxocarbonium ion, because if this type of intermediate is not formed, then we won't get this type of product while adding the SO3 2-, because in this case the OH2 is directly the oxygen, the water is directly removing the OR from the system. So there is no such case formation, there is no such probability of formation of that type of intermediate, while just by adding a sulfide anion we can get this type of intermediate, which supports that formation of this oxocarbonium intermediate in the reaction mixture. So this one is this much for today's class. So I will just give an overview of everything. So first we solved one question based on that rho value or Hammett equation. Then we solved some question based on kinetic isotope effect, and we discussed about other different type of kinetic isotope effect like secondary and its origin, and we solved some example based on that. Then one question we gave, which you guys could try by yourself. I will solve this one in the next class. Then we solved some other problems. Then we discussed about equilibrium isotope effect and their use. Then we talk about isotope leveling experiment and solve some question based on that. Then we discuss about intermediate trapping and how it helps us to know about the reaction mechanism, and we solved one question which is based on discussed here. Okay, so this much for today's class. Thank you everyone. I hope you guys are learning from this session and solving some more questions based on this topic. Next session I will come up with some more questions and new problems where you can get a greater idea which have been discussed by ma'am. Okay, thank you everyone. Have a nice day.